So we want to notice that we have assigned our vertical and horizontal stretches to A and B respectively. So the vertical stretch is controlled by A. So A is telling us about the amplitude. Our horizontal stretch is controlled by B. So B is telling us about the period. You have to do a little bit of work to get at the period. We take 2 pi and divide it by B, figure out what the period is, instead of just looking at what the absolute value of the number is, figure out the amplitude. Now we want to move on to the shifts. We want to look at make changes in the vertical and the horizontal with the shifts. So we've got 2 left. We've got C and D. So let's go over to our graph. Let's hop over to our graph and check out some changes in C and D. Last time we observed that if we put D in motion, the graph goes up and down. Okay, that's a little bit too much. No, too far, come back. Okay, thanks. Okay. Now we can see, no, too far. Let's calm D down a little bit. Chill. Okay, now go in motion. And then it goes all slow. That's because that is the same range to go through, right? I don't know. We're going slower. Maybe it's the same, but it's just throwing it off. Doesn't matter. So we can see that the amplitude, the period, and the horizontal shift aren't changing. So it looks like D is in charge of the vertical shifting. So let's jump over to our table and see that D, which was a light blue, is in charge of the vertical shifting. The vertical shift doesn't affect the amplitude. The amplitude is the distance from the middle to the top, but the vertical shift affects where the middle, the top, and the bottom are. So moreover, if we look at the graph, which I left running, the value of D is always going to be at the middle of our graph. So I put not only the, well, I also switched from cosine, from sine to cosine for reasons. So as we're running D, we can see, if I run the horizontal line, y equals D, we can see that that constant term at the end, the plus D, is identifying where the middle of the graph is. So we've got even more detail now. D, whatever value of D we have, that's where the middle is going to be. So each of these numbers is telling us something. So if we see +1, we know that the middle of the graph is at 1. If we see -5, we know that the middle of the graph will be at -5. Any questions? Everybody focus on this graph. It slowly moves up and down. Focus on it. Focus on it. I'm not trying to get it right. It's a math class. You're getting sleepy is the default setting. Pause. That's just good. So that leaves one number to tell us what's going to be going on with our horizontal shifting. So there's only one left. So C must be in control of the horizontal shifting. Let's check out the horizontal shifting. There's with a C of 0. So that vertical line is going to be where the graph is starting. So the other reason I switched to cosine is I want to start at the top. It's easier to see starting at the top rather than going up.
So if I animate C, or if C increases, we can see we're shifting the graph to the right. And then when C decreases, we just shift the graph to the left. So if we put C in motion, oh, there, barely fits negative 10 and 10. We can see C is just dragging that top where we think of the start is going back and forth. The weird thing that's going on here is that when the equation has a +5, the whole graph moved up 5. But then to move the graph to the right, we had to say x minus 5. So when we pause C at 5, I missed. That was unnecessary. When we pause C at 5, the equation says x minus 5. So in the parentheses, it says b times x minus 5. And that took the starting point and moved it to the right, even though the equation says minus 5. Yes. Yes. Eventually, we'll just get a copy. So let's draw another a cosine of bx. Oh, that's too severe. Let's pick a happier color. I already used green. I need contrast though, red. We'll go, or blue. We'll go with blue. So if I put C into motion, C starts to shift over. And when C gets up to 10, everything lines up again. This is because I've shifted the value of C. The horizontal shift is now the same as the period. What's the period of my graph? Let's see, here's the top at 0. So I set the period of the graph to be 10. So when our horizontal shift gets to the period, we just get a copy of the graph. Then we have all these values in between, and C goes down to 0. That's the same. But when C I'm going to run out of space. There we go. When C gets down to negative 10, I've shifted the graph one full period, and they line up again. So we're only really going to care about horizontal shifts that are less than one full cycle. Any questions? I like the orange and blue together. That looks nice. So what we want to notice is what we want to notice is that we can think of the whole, even though the graphs go on forever in both directions, we've been referring to them as having certain starting points. So cosine we think of as starting from the top. That's just the point in the middle. That's where their 0 is. So if I change C equals 1, if we have cosine of x minus 1, we have moved the starting point over to 1. If I change C to 2, now that top point is at 2. If I change C to 3, that top point is up at 3. Then if I change C to negative 3, my top point is now at negative 3. So where D, the vertical shift, is the middle, the horizontal shift is where we put that starting point. So cosine starting at the top, that's where we would draw the top. So if it said x minus 4, then we would put the top at 4. Any questions? How's everybody think? One last thing to observe. Let's switch back to. So C is where we're going to put the start. Either the top, the mid going up, and the bottom, and the mid going down. A positive sign starts at the top. Starts at the middle, going up. No, it's just where for cosine, that's where we're hitting the top of the graph. So that'll be where C will be the location of where the maximum is, not the actual maximum itself. Each of our 4 points that we use as to locate where our graph is, top, the middle going down, the bottom, and the middle going up. Each of those correspond to either a sine or a cosine with a plus or a minus. Positive cosine starts at the top, so a negative cosine starts at the bottom. Positive sign starts at the mid going up, so a negative sign will start at the mid going down. C will tell you where to put that start. So that'll be along the X, the horizontal. Last thing we want to look at is the 2 operations that we used in doing all this. Notice that our stretches, vertical stretch was A, horizontal stretch was B. If you look at the equation and how A and B are included, A and B are coefficients, which means they're included by multiplication. Multiplication is what causes the stretch. Notice that C and D are included by addition. A plus B and a minus a negative C. Or plus a negative C. Addition makes shifts. Adding and subtracting shifts, that's a terrible word. Shifts things around. Multiplication is what stretches things. The other thing to note is that when we had a vertical stretch, when it was bigger than 1, things got bigger. Bigger number, bigger stretch. But horizontally, bigger number, compression, more compression. It's like the horizontal goes opposite. Same thing with the shifting. When the vertical shift was positive, plus D, things went up. But when the horizontal shift, we write it as X minus C. So X minus 5 goes to the right. That seems a little bit opposite, because normally right is our positive direction. So it's like the horizontal ones do the opposite. Last thing to notice. This is part 3 of the last thing, so it's not like another last thing. This is not the ending of, Lord of the Rings trilogy, where it just keeps going. Notice that B and C are operations of multiplication and addition that happen before we look at the sign. If we think of the order of operations about what happens to X, first we subtract C, then we multiply by B. Now we're at the sign. Stuff that happens before sign has a horizontal effect. Stuff that happens after sign, multiplying by A and adding D, that has a vertical effect. Before the function, horizontal. Okay. After the function, vertical change. So horizontal stuff, because the operations are before sign. The vertical stuff is operations after sign. That seems like it's a lot to remember, but that's only because it's a lot to remember. But you don't have to remember all of it yet. The 4 pieces that you need to identify. Amplitude, period is 2 pi divided by this coefficient. Horizontal shift, vertical shift. Amplitude, middle, use this to figure out the period. Use this to determine where you start. Those are the 4 things that you have to know. Good questions? Then you can start doing things like no, B isn't equal to the period. B tells us what the period should be. The period is 2 pi divided by B. If we take X and we square it, it makes infinity show up faster, and that's why it's compressing in. But notice that the square happened before the sign, and so notice that all the change was horizontal stuff. There are horizontal shenanigans going on here. By the 0, it's mirroring, because all the negative, the squaring things takes all these negatives and makes them positive. Notice that if I switch the squaring to happen afterwards, I've taken all the negative stuff and made it positive. Vertical shenanigans have happened here because the squaring happened after the trig function. Oops. Hello, cosecant squared. Oh, that one's just weird. This one, yeah, Decimus is like, oh, the fuck you doing, man? Come on, man. What happens if we do X to the -2? So if X squared makes infinity show up faster, but 0 squared is 0, right? But if we do X to the -2, that makes it reciprocal. That's a 1 over X squared. So I've taken 0 and moved it to infinity and moved infinity down to 0. Now that 0 is down to infinity, what's happening here is that we're trying to cram an infinite number of oscillations before we get to 0. And that's why the graph is getting all crammed up over here. So if we try to zoom in, and it's just like, oh, come on, man. And you can watch my computer struggle with this. Because it's not just making everything blue, it's actually trying to draw all these blue lines. And the fan's like, oh, come on, man. I'm an 8-year-old MacBook Pro. I can't handle this. I'm like, well, zoom in more. And eventually the calculator will just say, forget you. Fractions are just, don't change things very much, right? Because if we have like, let's get back to normal space. So if we have like x squared, right, that's just a parabola. If we do a fraction, x to the 2.5, that's just kind of similar. We don't get to have the negatives because of the 0.5, but if I do like a 0.5, then I get to do some negatives. Because that's a 1/5 power. Sometimes we don't get to use negatives in exponents. They're still there. We can't see them because they're not, everything that we see here is a real number. And when we get to something like the square root of -1, we get a complex number, an imaginary number. And that's why it's disappearing sometimes. Any questions? All right, that's going to do it for today. That's going to do it for this week. We'll have some homework on graphing, sinusoidal functions. I'll see y'all on Tuesday. Everybody have a good weekend, and thanks for playing. Yeah.